Last class we have discussed about the experimental arrangement. Now we will discuss about the theory. Means how to do this experiment, how to perform this experiment. Okay, now they have performed this experiment at different voltages. They have done this, Davisson and Germer have done this experiment with different voltages. What they have taken is, here this is the direction of scattering. Direction of scattering is represented by pi. So this is the direction of scattering phi. So first they have placed detector D at 10 degrees. They have placed this detector D at 10 degrees. So at 10 degrees they have considered the direction of scattering. Direction of scattering is taken by phi. Next, intensity. Intensity of scattered electrons is measured by galvanometer deflection. So what they have done is, at certain voltage they have taken at 10 degrees, they have noted the value of intensity of scattered electrons. Later they have moved detector through 20 degrees. 20 degrees they have taken the reading. Next, they have taken the reading at 30 degrees. They have taken the reading at 40 degrees. Like this, they have done the experiment for different voltages. At different voltages, they have done the experiment and they have plotted a graph. They have plotted a graph between direction of scattering, phi, and intensity of scattered electrons. Okay, so the electron detector D. D is moved over the circular scale for given accelerating voltage. For certain voltage, they have moved electron detector throughout the circular scale. So the variation of intensity of scattered electrons. The scattered electrons are measured with respect to direction of scattering. With respect to phi, they have measured intensity of scattered electrons. So at voltage 54 volts. So at the voltage 54 volts, for the voltage V is equal to 54 volts, and for the first order diffraction, the order of diffraction is 1. So for the first order diffraction, they found that angle of diffraction is maximum. It is maximum. See here, it is maximum at 50 degrees. It is maximum at 50 degrees. So they have done experiment for many voltages. They found that at this voltage, the angle of diffraction is 50 degrees. Now, so see here, under this condition, so see here, these crystal planes, we know that these are the crystal planes. These crystal planes looks like grating. Grating means number of slits placed side by side. So like that only we have crystal planes. This is the nickel crystal. So what happens here? Electron beam comes and falls on crystal plane, nickel crystal. When electron beam falls on nickel crystal, it gets diffracted. The maximum angle of diffraction is found at pi is equal to 50 degrees. Maximum angle of diffraction is 50 degrees. Okay, now see here if I make this half, so what is this angle? This angle will be 25 degrees and this angle also will be 25 degrees. Now what is angle of diffraction? Here what is angle of diffraction? Theta. Which one is angle of diffraction? This one is angle of diffraction. So how to get angle of diffraction? Now angle of diffraction theta is equal to, now how to get, this is 90 degrees, and this angle is 25 degrees. So 90 minus 25 means pi by 2. 90 minus 25 degrees, which is equal to 65 degrees. So I got angle of diffraction theta is equal to 65 degrees. So what I have done, these are the crystal planes. These are the crystal planes. When electron beam falls on the crystal planes, it gets diffracted. Maximum angle of diffraction is at 50 degrees. So if I make this half, this is 25 degrees and this is 25 degrees. And if this angle is theta, what is theta? So theta will be 65 degrees. Now, so I got n is equal to 1, theta is equal to 65 degrees. See here, the interplanar spacing, the D means the distance between two planes. The distance between two planes, interplanar spacing of nickel crystal is found to be 0.909 angstroms. From the X-ray diffraction method, the interplanar spacing of nickel crystal is 0.909 angstroms. Okay, now we know Bragg's law. What is Bragg's equation? What is the Bragg's equation? 2d sine theta is equal to n lambda. 2 into what is d? 0.909 angstroms. So you can keep it as angstroms, or otherwise you can keep it as 10 power minus 10. So 2 into 0.909 into sine 65, which is equal to first order diffraction, 1 into lambda. So if you calculate, you'll get lambda is equal to 1.65 angstroms. This is the value we got from experiment. So this is the experimental value. Now, this experimental value should match with theoretical value. What is the theoretical wavelength? De Broglie has given expression for theoretical wavelength for electrons. For electrons, de Broglie's wavelength is lambda is equal to 12.26 by root V, which is equal to 12.26 by what is the potential difference we have taken? 54 volts. At 54 volts, the maximum diffraction occurred. So this 54, root 54, if you calculate, you will get 1.67 angstroms. So this is the theoretical value. So see here, experimental value we got 1.65 and theoretical value we got 1.67. So there is very good agreement between experimental value and theoretical value. So what does it prove? It proves particle exhibits wave nature. So it proves particle exhibits wave nature. Which particle exhibits wave nature? The particle taken is, here particle considered is electron. Electron exhibits wave nature. Okay, so this is about Davisson and Germer experiment. See here, they may ask in the question, establish an experiment to prove that electron exhibits wave nature. So see here, indirectly they will give the question, establish an experiment to prove that electron exhibits wave nature, means this is the experiment we have. Okay, so this is about Davisson and Germer experiment. Thank you.